Select the major product of the following reaction sequence. So if we look at what we are starting with, we see that we have an alkene. We have that carbon-carbon double bond. And then we see a two-step reaction sequence that we're going to undergo here. So the first step we see is MCPBA. And so this is metachloroperoxybenzoic acid. So this is a peroxy acid. And what a peroxy acid does when it encounters an alkene is it converts the alkene into an epoxide. So after the first step of this reaction, we should have an epoxide. And epoxides are cyclic ethers. In general, ethers are not reactive, with the exception of epoxides. So what makes epoxides reactive is the fact that we've constrained them into these three-membered rings. We have a lot of angle strain in this system. These are all sp3 hybridized carbons. They would prefer to have a bond angle of 109.5 approximately. And we're squeezing them into this little triangle shape where we've got these 60-degree bond angles. So these are really susceptible to ring opening reactions. So what we have in the second step is the conditions to do a ring opening reaction. So you want to notice that we've got acid. We say H+, so that's probably a catalyst like sulfuric acid, a small amount of that, or maybe a small amount of hydrochloric acid. And then we've also got methanol as a really weak nucleophile. So it has about the same nucleophile strength as water. So when it's neutral, methanol, it's a weak nucleophile. If you were to deprotonate that and make it the methoxide, then it'd be a strong nucleophile. But as it is, it's a weak nucleophile in acidic solutions. So the first thing that's going to happen is your epoxide will be protonated. And so what this does is it makes that epoxide even more susceptible to nucleophilic attack, such that even a weak nucleophile like the methanol can do the opening reaction of the epoxide. So the question is, with this unsymmetrically substituted epoxide, is where does the nucleophile attack? Is it going to add to the least substituted carbon atom, or is it going to add to the more substituted carbon atom? And under acidic conditions, we've got a bit of a positive charge building up on these carbons, and we would expect to see more of a positive charge on the more substituted carbon atom. So with acid and epoxides, we see the ring opening at the more substituted, so it's going to open at the more substituted carbon atom. So we expect that the methanol is going to attack this secondary carbon atom, popping open that ring. And so we would see, so on the end carbon, we have that alcohol attached. The methanol has attacked here. And then a final proton transfer step should remove this hydrogen. So we're going to assume that the reaction conditions are such that we're probably using methanol as the solvent. So we have a large excess of methanol around. So it can take that proton. And so that would give us this structure A, where our weak nucleophile has added to the more substituted carbon atom. And it's the acidic reaction conditions that tell us that.